All right, guys, today we are going to start our very last unit of the year over quadratic functions. So today we're going to talk about what a quadratic function is and how to identify it, essentially. So here's our definition. Quadratic functions are any function that can be written in the form ax squared plus bx plus c. So essentially what you're looking for a quadratic function in terms of an equation is that its highest exponent is an exponent of 2. Okay, so this is a graph of just y equals x squared. This is what we call the parent function. It's the most simple version of a quadratic function, so it doesn't have to have all three terms, but it does need to have an exponent of 2 and no exponents that are higher than that. The U-shaped graph is called a parabola. So quadratic functions make this U shape that we call a parabola. So how to identify a quadratic function? When you're looking at the equation, again, you're really just looking for an exponent of 2. So when you have an equation, it's a little bit easier. But I'm also going to show you how to identify it from a table. So on the left-hand side here, we're going to talk about linear functions first, since we already know about linear functions. So here it says linear functions have constant first differences, and I'm going to show you what that means. So I'm going to go ahead and fill in my table with 5 points. You can pick anything for x, so I'm just going to pick from -2 to +2, and I'll plug it in to get my y values. So here, -4 plus 3 would give us -1, -2 plus 3 is 1, we'd have 3, 5, and 7. So I just plugged in my x values to get my y values out. For the most part, our tables will already be filled in for us. But what it means to have constant first differences, that means if I go down my y's here, this is increasing by 2, increasing by 2, increasing by 2, increasing by 2. It's the same all the way down. This is increasing by 1, 1, 1, and 1. So this is how we would check if something's linear. If we want to check if something's quadratic, we need to check for constant second differences. So up here, quadratic functions have constant second differences. So I'm going to go ahead and fill out my table here again. I'm going to kind of speed through this part. If I plug in a -2, I would get 12, 3, 0, 3, and 12. Like I said, for the most part, our tables will be filled in for us, so you don't have to worry as much about that, but I am getting these values by plugging in these numbers for x. So when we look at our difference here, I went down 9, down 3, up 3, and up 9. That's how I'm getting from one to the other. If I do that again, though, from -9 to 3, that's +6, +6, and +6. And now the second time I do it, they're constant. So that's how we can check if we have a table, if they are quadratic or linear. So now we're going to do a couple examples. So in this case, I have a table. So let's check and see our first and second differences to see if it's linear or quadratic. So here I'm going down 6, down 2, up 2, and up 6. So if I do this again, I'm going up 4, up 4, up 4. So that is constant second differences. So we would say that yes, this is quadratic. For an equation, again, you're just looking for that exponent of 2. You do have to have an exponent of 2 and no exponents that are higher. So here, y equals -3x plus 20. There's no exponent of 2. This is just linear. And then our last one here, we do have an exponent of 2. And more specifically, that has to be on our x. Has to be on our x, because most of the time we'll have y equals, like this can be rewritten as y equals -3x squared minus 4. So it does have to be on our x. But it does have that exponent of 2, nothing higher, so it is quadratic. Graphing quadratic functions. So to graph these, we are just going to make a table, kind of like I was doing before. We're going to plug in these 5 values to get the y values, and then we can plot our points to make our picture. Later on in the week, I'll show you more shortcuts on how to graph these, but for now, this is the only tool we have. And really you can use this trick to graph any function no matter what it is. So if I plug in a negative 2 squared is 4. 4 times 2 is 8. If I plug in a negative 1, I'll get 2 out. If I plug in 0, I'll get 0 out. If I plug in 1, I'll get 2. And if I plug in 2, I'll get 8. Okay, so then we can plot our points. We have 0, 0, negative 1, 2, negative 2, 8, 1, 2, and 2, 8. And then you just want to do the best you can to connect those with your U shape. Again, we call these a parabola. This one is going to be very similar, and we chose two very similar ones on purpose. I'll show you why in a second. So if I do my table, just all of these are going to be negative instead of positive, my y values. So I'm going to go ahead and plot these now. And connect them. And the main thing we wanted to show here, or why we did two that are almost identical, is the only difference here is the sign in front of our x squared. But this positive one opens up and this negative one opens down. So on our next slide here, it says, identify the direction of the parabola. So positive is up. We'll put that here. Positive is upward. Negative is downward. And for these, it's after we isolate y. Because we're trying to get standard form. Standard form is where we have y equals ax squared plus bx plus c. So this one's already in standard form where y is isolated, and my leading coefficient is positive. So this one's going to open upward. Here I'm going to need to isolate my y, so I'm going to move this 2x squared to the other side. And I'll have y equals negative 2x squared plus 5. Well, this one's leading coefficient is negative, so it's going to open downward. Identifying the vertex and the minimum / maximum. Vertex is the center point of your parabola, so the very middle. On either side would be a mirror image here. So vertex is the very center point. If your graph opens upward, it has a minimum. So this would be an example of a graph with a minimum of 0. You would just say what its y value is. The very smallest y it has is 0. If it opens downward, it has a maximum. So if it's upside down, because it has a negative leading coefficient, it's going to have a maximum instead. And in this case, its maximum is 5. So there's a couple examples there. All right, last slide here, domain and range. We have to remember back to domain and range when we did our functions unit in the first place. So domain is talking about your x values. Range is talking about your y values. For domain, on every single quadratic problem, because this is going on forever, left and right, our domain is always going to be from negative infinity up to positive infinity. What's going to change is our range. So if it opens upward, this one opens up, it's going to go on forever to positive infinity. Let's go ahead and start this one too. My domain is going to be from negative infinity to positive infinity always. But this one opens downward, so its lower bound is going to be negative infinity. So upward, you want positive infinity on the right. Downward, you want negative infinity on the left. Now to find this other value here, you have to look at your minimum and maximum. So here, this has a minimum, and its minimum is 1. You're looking at the y value here. The very lowest it can be is positive 1. When it opens upward, you have a maximum, and the very biggest it can be is positive 4 here. Okay, so those are our domain and range for these two. Okay, that's the end of our notes today. You do have a short delta math assignment to work on where you are just identifying if the equations are quadratic or linear.